So I wanted to come back to this because I think these are some really cool proofs. So let me explain why this length is sine, this length is cosine, this length is tangent, and that length is cotangent. Okay, so let me figure out what is the length x and what's the length y here. This is a right triangle, so by the definition of sine, the sine of alpha will be the length of the opposite side of the right triangle divided by the length of the hypotenuse. So the sine of alpha is x divided by 1, so it is x. So x is just the sine of alpha. Similarly, for y, if I use the cosine of alpha is the length of the next side divided by the length of the hypotenuse. So the cosine of alpha is y divided by 1, so it's just y. So those are the easy ones. This is cosine of alpha. So let's figure out what's z. Okay, so now let's figure out what is z, the length from here to here. The key is to realize that there are many right triangles here. This is a right triangle, but this here is a right triangle also, and so is this one. This is also a right triangle, which gives us a few right angles. This is a right angle, this is a right angle. Since this is 90, this one and this angle here, I'm going to call beta, those have to add up to 90, but this one and this angle here add up to 90 also, so this angle here is alpha. And now I can use this alpha to compute sine and cosine and try to figure out what z is. I already know that this side here is length sine of alpha, so that tells me now that the cosine of alpha will be the length of this side, sine of alpha, divided by the length of this hypotenuse, which is z. And therefore, z is sine of alpha divided by cosine of alpha, which is tangent of alpha. So z is length tangent of alpha. And I'm going to leave it up to you to figure out why this length from here to here is the cotangent of alpha, and for that you can use this triangle here.